I don't want to do that because then I won't be able to see anything. Exit full screen. Nope, don't want to see that either. All right. Everybody got their notes ready to roll? Emily, feel free to go back and check those notes, the video yesterday, and let me know if you have any questions. But we're going to carry right on with your nerves here. Okay. For my folks at home, I guess the video's already started. We edited the video, whatever. Let's carry on. So we have, yesterday we ended up talking about this guy right here, the action potential. It's all about, and I'll let the folks at home know as well. They'll get you a good YouTube video on this stuff. I try to be artistic with my stuff. I try to show some pictures here, but a good YouTube video can show you this with animation a whole lot better than just trying to do it by talking over the internet. So the big key I want you to take away from this is if you did not have myelin, your nerves would not be able to travel fast enough. You could not send the signals fast enough to your body parts. And since you have so many competing signals happening all the time, think about all of the different individual muscle movements that it takes to balance and walk upright. All of the hundreds, thousands of different nerve signals I'm sending just doing what I'm doing right now. Now think about if all of those nerve signals were even just a little bit slower, how my body would get confused really, really quickly, and I would lose balance, and I wouldn't be able to communicate, and I wouldn't be able to do all these things. Think about the talking, pulling those little vocal cords and combining that with the diaphragmatic pressure to be able to push out air. If our nerve signals even traveled a smidgen slower than they are, you'd be paralyzed. You'd be paralyzed, you wouldn't be able to talk, you wouldn't be able to move, you would deal with numbness, and that's a huge thing that a lot of your nervous system pathology has to do with the myelination. Okay? So carrying on. So once you hit the end of a nerve, you get to the synapse. This is what we talked about yesterday with the Zoloft commercial. Zoloft commercial showed that synapse where you had the end point of one nerve meet up with the dendrite of the next nerve. And so when that signal gets to the end, chemical or electrical channels are going to open where you have these neurotransmitters that are just sitting in the terminal endpoint waiting to go. They're just sitting there. And so what they do when the signal gets to them is they slide over here to the membrane, and they're made, these little vesicles are made of the same stuff that your cell membrane is made of. And so they just grab a hold of the cell membrane and then just become a part of the cell membrane. And all of the stuff that was inside them now has been opened and is released outside of the cell. That stuff's going to release outside of the cell and then attach chemically to the dendrite on the next cell and then start a new action potential. Now, as long as these guys are hanging out here, you're going to keep sending that message. But you have these reuptake channels on the side where these guys are going to be kind of go around in the open space and be taken back up. And so when the nerve signal stops, those neurotransmitters get taken back up and you can keep using them over and over and over again. And this, like we talked about yesterday, is where you put your drugs. This is where you put your medicines. Like Zoloft is going to do this with serotonin. It blocks the reuptake, so the serotonin stays out there and it keeps you happy. Cocaine does it with acetylcholine. So it blocks the reuptake of acetylcholine, and every little signal you send, it just keeps sending it over and over and over again. And that's why you stay awake for like 2 days and do all kinds of things. And thus the mechanism of function for cocaine. Methamphetamine does some similar things as well. Okay? So once you get down there and you attach, you're going to start talking about your new signal and you carry on. So you're looking at your notes there. neurotransmitters begin a new action potential on a new nerve. The common neurotransmitters, I'm not going to say, hey, tell me the neurotransmitter that does this. Hey, tell me the neurotransmitter that does this. But I might say, what is acetylcholine? And you can tell me, hey, it's a neurotransmitter. So be able to recognize these guys right here. Acetylcholine is for movement. Dopamine and serotonin have to do with your brain signals, kind of your feeling good or feeling depressed, how much of that you have. And then GABA is it's short for a big, long, crazy name, but it is a neurotransmitter that has to do with reflexes. Cool? Carry on. So I told you when we started this that we'd finish up with the central nervous system, and that's what we're going to do now. We're going to go back and hit the central nervous system, which is your brain and spinal cord. Spinal cord, you have different levels. Years ago, when I first started teaching this, I would actually break down a transverse section of the spinal cord and talk about the dorsal root ganglia and the different things going in and out of the spinal cord. But then I kind of got to thinking that was a little bit too beyond our level. And so I'm good just talking about the spinal cord as a housing unit for the nerves that are then going to leave and be all the nerves in your body. Biggest thing you need to understand about the spinal cord is dermatomes. Anybody know what that is? Oh, you let me down, James. Look at the prefix, which is, okay, dermatomes are areas of the skin that are going to be sensory related to a specific level of the spinal cord, okay? So you guys are lucky enough to have lived in a time where anybody here got chicken pox when they were little? You know why you didn't? Pretty easy. Why do you not get any virus? What did you get? Yeah, you got a vaccine. When you were little, they had a chickenpox vaccine. You guys got a chickenpox vaccine, so you didn't have to deal with chickenpox. Well, we didn't have a chickenpox vaccine when I was little. And so when I was little, poor little 6-year-old Mr. Tire is standing there with the chickenpox. And for some reason, my mama wanted to take pictures. And so we have a picture of me with chickenpox and a cowboy hat and nothing else. And like, I'm trying to smile, but I'm hurting because it's not a very fun disease, because it's these itchy red bumps that just hurt, not just itch, but hurt. And so what's interesting about chickenpox is called by, anybody know the virus? Chickenpox is the common name, but anybody know the virus? Nope. Varicella zoster. Okay. Varicella zoster virus. Once it's done, once it runs its course, you don't get cured from it. The virus, your body doesn't beat the virus. What happens is your body fights off the virus, and the virus goes and hides. The virus goes and hides in the dorsal root ganglia of your spinal cord, and lives in your spinal cord. Right now, I have varicella zoster virus living in my spinal cord, doing like this, just waiting, just biding its time. And one day when I get hurt, or when I get sick, or when I get old, the virus is going to say, now is the time. But it's only on 1 or 2 dorsal root ganglia. So I'm going to have, depending on what level it's hiding in, I'm going to have a re-outbreak of that skin infection, but it's going to be in a stripe across my body. Anybody know what we call that? The return of chickenpox? Very good. Shingles. Shingles is when that comes back, and it's on a dermatome. Dermatome is an area of the skin associated with a spinal spot. Okay, so when you have spinal injury, one of the things they do is they take a little pin, not like a stab you pin, but like just like a probe, and just poke going down and make sure that you can feel every dermatome and test each dermatome. All right, so let's look at the brain though. The brain is going to be 2 main kind of shades of the brain. You have central gray matter surrounded by external white matter. On dissection, it is not gray and white. It is more yellow and beige, more like beige and brown almost. But we call it central gray matter and white matter just because that's a way to look at it. The darker area is mostly the somas, mostly the cell bodies. and the lighter area is mostly the axons. There's not as much stuff, so that's why you get the lighter color. Okay. You have the cerebrum, which is the main body of the brain, which is the pink in my hand, or the dark pink in my hand. It's normally what we think of as the brain, is the cerebrum. Then you have the cerebellum, kind of like a butt to the brain, the green part underneath here. And then you have the brainstem. Brainstem is going to be the top of your spinal cord, leading out of the central part of the brain. So cerebrum, cerebellum, brainstem. And you go to medical school, you can take a whole class where all you do is anatomy of the brain. First semester of medical school is gross anatomy, where we dissect a person. Second semester of medical school is neuroanatomy, where all you do is the brain and spinal cord. So you know, I joked that first, I didn't really joke, but I talked that first couple of days about not being happy on that first level. Realize there's a whole bunch more levels we could go on this that we're not going to go because we don't have time. Okay. Look at the ventricles. We talked about that the other day. Ventricles. Every open space in this, that from the skull to here, is ventricle. You have ventricles that run down the middle. You have ventricles in these little crooks and crevices. You have ventricles underneath and everything. Those are what's going to be filled up with cerebrospinal fluid. CSF, it cushions the brain. They are continuous, which means their cerebrospinal fluid can flow everywhere. They are not continuous with your body because you have the blood-brain barrier. You don't want things that are able to be in the blood out here, up in your cerebrospinal fluid up here. Why? What are you worried about? What do you absolutely positively not want to happen? Why do we keep this and the stuff that can flow through this separate from this and the stuff that can flow through this? I got something bad flowing through my vessel in my arm, and I get an infection in my arm. I don't want an infection in the brain. Let's talk about why. If I get an infection in my arm, what is the worst case scenario? I lose my arm. If I get an infection in my brain, what's the worst case scenario? Y'all with me? Okay, so cerebrospinal fluid is continuous, but is only continuous with itself. It flows around the brain and spinal cord, but nowhere else. Okay? Looking at the cerebral hemispheres, everybody knows what the brain looks like. You have the ridges and the grooves, and they have a special name. The ridges are called gyri. The raised portions are gyrus. If I was to talk about that ridge right there, it's a gyrus. All of the ridges are gyri. And then every little groove, every valley in the brain is called a sulcus or sulci. So gyri and sulci. True or false? Every time I learn something new, I get a new gyri. Very good. It's false. We all have pretty much the same shape to our gyri and our sulci. Now, there are some diseases or alcoholism that take your brain and really smooth it out. And so there is some connection with having a wrinklier looking brain and being more intelligent, but you don't add more wrinkles, like macroscopic wrinkles. You just have more defined gyri and sulci. Does that make sense? And from a microscopic viewpoint, I guess you could say you do add wrinkles because you do add connections, but that is hyper microscopic. You wouldn't be able to see it on an examination. All right, so to kind of sum up what I just said, on autopsy, it would be really hard to say this person was smart. You probably could say this person had brain damage. Does that make sense? It's easy to look at a brain and say this person was having brain problems. It is hard to look at a brain and say this person was intelligent. Make sense? Okay. There are two hemispheres of your brain that are separated by a longitudinal fissure. Okay, I'll show you what I mean here if I can get my cerebellum from falling off. All right. two hemispheres of the brain, two halves of the brain, and running down the middle of the brain is this longitudinal. What does longitudinal mean? This way, not this way, okay? So running down the middle of the brain is this longitudinal fissure. Longitudinal just means that way, and fissure just means a valley, okay? So you have this longitudinal fissure, and really it goes all the way to this guy right here, which is called, holy crap, it's escaping me, the arcuate facilicus. That sound right? No. Ah, crap. Well, you have this little dark pink guy right here. It's going to communicate with both sides of your brain. Arcuate facilicus. I'm pretty sure that's right. Might be wrong. Love you guys to death. Arcuate facilicus. That sounds right. Okay. Obviously, it's not on the board, so I'm not going to put it on the test, but there you go. I don't want you to know very, very specific parts of the brain, and I'm not going to ask you to label a brain because it's not up there on the board, but I do need you to know that it is kind of separated into lobes. You have the frontal lobe, pretty straightforward. Anybody, what psychiatry class story was made famous by the frontal lobe? You remember his name? What was that? Shamir said you were in psychiatry, right, Shamir? Yeah. You remember his name? Psychology. Huh? The guy who, he said train wreck dude? You remember? Oh man, did you finish psychology? Yeah. And I didn't talk about Phineas Gage? Phineas Gage is one of the coolest medical stories. Rest in peace, Phineas Gage. But it's one of the coolest medical stories, sad story, but cool. Because the brain is one of the weirdest things to study. Okay? If I was a really mean doctor 1,000 years ago, I could study all kinds of body parts. I'd go get me a prisoner or a beggar or somebody, and I take them to my lab and I start cutting them open, and I can see all kinds of parts working, right? The brain is a whole lot harder, because as soon as you get to the brain, what do you got? A dead person. You with me? Everybody understand? So the brain is really, really hard to study, because once you get to the brain, now your subject is dead. So Phineas Gage was really, really important in this idea of localization of function in the brain. And here's what I mean by that. So quiz bowl here. So let's see if James knows this. Anybody ever heard the phrase, I think, therefore I am? Oh, come on, I need to pay for it. That's a very, very, very famous philosophical thing. You remember his name? I think, therefore I am. You didn't know that. His name is Rene Descartes. Descartes was the philosopher. And Descartes said, I think, therefore I am. I can think about what I am, so there is something about me that is mystical and magical that science will never be able to explain. And it was this idea that the mind was not something that we could really quantify, like the heart pumping blood or the stomach digesting food. The mind is something just otherworldly. I think, therefore I am. I'm something, there's something different going on. Well, this guy named Franz Joseph Gall came along, and he said, Rene Descartes, you're wrong. You think, yes, but you think because of your brain. Not only that, but there are certain parts of your brain that are going to make you think in different ways. Now, Franz Joseph Gall wasn't exactly right either, because he came up with the idea of phrenology. Anybody ever, phrenology, P-H-R-E-N, phrenology? You've probably seen this picture if you don't know what phrenology is. Phrenology, every once in a while you'll see a model that maybe looks like this guy right here, where you have a model, and if somebody has a bump right there, that means they're really good at math. If they have a bump right there, that means they're a really good musician. And you know, this idea that you can localize different functions on the brain. Okay. Now, Franz Joseph Gall was wrong. I can't feel James's skull and say that he is anything. Okay, because you're not feeling the brain, you're feeling the skull, which is not the same thing. But he was right about localization of function. And we found out, and it was confirmed with Phineas Gage. Phineas Gage was working on the railroad, like James said, and he caught a railroad spike, went past his nose, up through his brain. And he survived. They took it out, and he made it. Prior to getting hit with the railroad spike, he was the foreman. He was a really good leader. He was able to get people to come and work for him and inspire people. And he was a friendly dude. And after, he would curse people out for no reason. He was grumpy. He couldn't lead people. He couldn't work his job. Who he was literally changed because of an injury to his brain. So Franz Joseph Gall, years later, was proven right by that case. And then there's been other cases since, but that was really the first groundbreaking case that kind of said there are certain things about who you are because of certain things going on in your brain. Okay? So we have 5 lobes. Frontal, parietal is going to be kind of the superior part of your brain. Temporal, on the temples, on the sides. Occipital is kind of the posterior part of your brain. And then insula are these kind of extensions going down off the bottom of the brain. Once again, I'm not asking you to label the brain. Just know we got lobes, okay? And then another thing that you could go into if you ever take neuroanatomy is all the cortexes. There's all kinds of different cortexes that we've discovered that this part of the brain controls this part of the brain controls this part of the brain controls this. I'm going to talk about 4, okay? The first one is the primary motor cortex. The primary motor cortex is this big, straight up and down gyrus right in the middle of our brain. The primary motor cortex. Now you could probably guess just by the word there what the primary motor cortex does. It's the most important part of the brain for moving. Okay, skeletal muscles moving. Okay, right beside the primary motor cortex, in this line that mirrors it, right beside it, is the premotor cortex, which is your learned movements. This is a trick question that everybody always gets wrong. Let's see if we can get it right or wrong here. The premotor cortex or the primary motor cortex? Where is the information for knowing how to walk located? That's probably true, that it is in both. Where is it probably going to be the most located? It's actually most in the primary motor cortex, because walking is not a learned behavior. Now, walking in certain ways is a learned behavior. Walking without thinking about it is not a learned behavior. Silly walking is a learned behavior. Make sense? Okay, and if you don't believe me, I have a test you can do with a baby. I always have some fun tests you can do with babies. When my daughter was a baby, I brought her into anatomy class and showed off tests because it's kind of silly. But like, people don't let me around their babies because I start doing anatomy tests with them. But next time you're around a baby that's not able to walk, so like we're talking before 1 year old, 3 to 6 months is the best time, because they're not baby enough that you're going to break them, but then they're definitely not thinking about walking yet. Make sense? So get you a good 4 or 5 month old baby, get them really good underneath the shoulders, and put their feet on a table, and then slowly bring them to you. Anybody have a guess of what you're going to see? Yeah, you're gonna, as you drag them, their babies are gonna do this. Because walking is something that is innate. It's something that's with us. It's something that's in our primary motor cortex. The reason babies can't walk is not because they don't know how. The reason babies can't walk is because they're born misshapen so that they can fit in the womb with their hips way rotated out. That's why when a baby does start learning to walk, they're wobbling all around because their hips are over to the side. Make sense? Okay. Premotor cortex is going to be shooting a basketball. Premotor cortex is swinging a tennis racket. Premotor cortex is writing your name. Make sense? Okay. Things that do not come innate, things that you have to learn. The other two are very important because they were early, along with Phineas Gage, they were early areas where really they confirmed Franz Joseph Gall's localization of the brain. You have these guys named Broca and Wernicke named these things after themselves, and Broca's area was motor speech area. What the motor speech area does is exactly what it sounds like. It's the movement of talking. If you have damage in your Broca's area, you can do a great job of writing down what you want to say. If you do sign language, you could sign exactly what you want to say. But the part of your brain that is forming the sounds doesn't work. Make sense? Wernicke's area, you can make all kinds of sounds, but you can't understand how to say something. So you can make all you can hum, like somebody sings a song with you, you can make the sounds and sing la 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 with them just fine. But being able to put the words together to understand what you're saying while you're saying it, these people have trouble writing what they want to say because they can't understand how to put together the language, how to put together the speech. They have trouble signing. And then every once in a while, you have a communication between the two that gets messed up, where you have somebody who knows what they want to say and they can make noise, but putting the two together doesn't work. So you have somebody who like you say, count to 10, and they might say 1, 2, green, 40, and just like and start losing and misunderstanding what they're trying to say because the connection between the two isn't there. So really interesting little things that we got going there. And there's all kinds of more cortexes. I just wanted to hit those big ones. Make sense? Okay. And finally there is the cerebellum. I'm not really going to get into the brainstem because that really gets crazy complicated. The pons medulla and the pons, the medulla, and the actual brainstem. But yeah. So cerebellum, right here on the back, its job is to organize the signals. And go back to what I was saying earlier. When I'm up here walking and talking at the same time, all of the thousands of different signals that are being sent to my arms and my legs and my waist and my core and my mouth and my neck are being sent all at one time. The cerebellum takes all of those hundreds and thousands of different signals and organizes them so that the thing flows. So that every single movement is not an individual movement. You show me somebody with a cerebellum that's destroyed, I'll show you somebody who can't do anything. Because every movement is individual. To think about how to walk with your cerebellum destroyed, you would have to think about every single thing you're doing individually, or else you fall down. And that's just, it's not functional. It's beyond possibility for most people. So cerebellum is all about organizing that information, getting that information to flow freely. We're going to talk a little bit about nervous system pathology tomorrow. We're going to go into our what can go wrong with the nervous system. I think that's pretty much it, though. Any questions? All right. Thank you so much. If anybody join us on the Zoom, let's see. No participants on the Zoom. So very sad.